Welcome. Thanks so much for joining us for this session on computing in the statistics curriculum, where we'll share some lessons learned from the educational sciences. My name is Matt Beckman from Penn State University, and this is a collaboration with colleagues you can see on the screen from the University of St. Thomas and University of Minnesota as well. And the goal for this session is really to introduce our audience to some questions, comments, considerations, things to think through for those that are introducing computing into a statistics course. So we're not trying to convince anyone to introduce computing into a statistics course, but if you have done so, it's important to think it through as you would any other learning objective in the course. All of us, the collaborators on this presentation, were self-taught programmers, but our students won't be. We're teaching our students, and so we need to be thoughtful about what should be different in their experience and how we can make the learning experience as efficient as possible for our students. One of those considerations from the learning and cognition literature is to manage cognitive load effectively. So cognitive load is this finite amount of information that we can process or store in working memory at a given time. And we can separate it into kind of two types. There's intrinsic cognitive load that is inherent to the content, the subject matter being learned. And this is really hard to change unless we change the content that we're introducing. We can't move the needle very much on intrinsic cognitive load. However, the opportunity is in extraneous cognitive load. So extraneous cognitive load is additional burden on the processing demand that a learner encounters when either there is gaps in the content, and so they have to kind of slow down and process things more carefully to try and bridge those gaps, or if the instructor is doing something that in some way is distracting to them. Like I'll share, we're going to be showing examples using R because that's the programming language that my colleagues and I have been using that developed the presentation, but these principles will be appropriate for any programming language, we hope. But R has many sub-languages of syntactic structures, and switching sub-languages, syntactic structures frequently can increase extraneous cognitive load for students. So some of the considerations that we'll be talking through, the syntactic structure I just mentioned, as well as normalizing things like debugging or parts of the computational thinking process that students just need to encounter and understand as a part of the problem solving that programming requires. Many students will find programming to be intimidating if they're especially accustomed to a graphical user interface like menu-driven interface to computing. So this can be intimidating to them, and it's important that we think through how to introduce it a bit more gently if we can, and to manage cognitive load so that they don't just feel adrift as they're learning to program in their statistics course. So some of the pedagogical decisions that are important to think about include logistical considerations that we'll need to account for, what will be taught, the scope that is demanded in the course, and how we'll sequence things. So some of those logistics might include, are students using a desktop installation or a cloud implementation, or both? Both would require more cognitive demand on students to be switching between these different paradigms. But there could be compelling reasons to do so in the context of a course. So it's just important to be thoughtful about these things. When and where do students need practice with the code? So is it happening more in class or out of class, individual environments, group contexts? Do they have templates with starter code, or do they have a blank document to begin with? Are they using R Markdown, or are they using R scripts? Those are all decisions to be thoughtfully made by the instructor, as well as how much they'll be introduced to code using live programming in the class versus worked examples or group activities where students are developing code until, as far as they can, until they get stuck, and then come together as a large group perhaps, and then students can continue in their groups. So again, different choices that can suit different courses or different objectives in different courses, but need to be thoughtfully chosen. What content do you start with when you introduce programming? Do you begin with data structures, kind of from the bottom up, that you're introducing vectors and data frames and then building towards more complex things? Or do you start with the cake, in Mina Cherenkaya-Rundell's vernacular, that you let them eat cake first and you show them cool data visualizations in EDA, and then you introduce the ingredients as needed. So you use that to motivate the other elements and the details. In choosing a consistent syntactic structure, doing so consistently lessens cognitive load. So when there is consistency among the syntax, students can focus on learning new functions. They can focus on what has changed if, you know, there's a larger body of the code that remains consistent. But if the code is constantly in total flux, then it's very challenging for students to process what's new and what is connected to things that they've already done. So for example, we consider if we're trying to decide between base or formula syntax or tidyverse, we might consider a simple example like we want to make a histogram of bill length from the Penguins data set. So you can see 4 different syntactic structures for producing that histogram of bill length from the Penguins data. And by comparison, they all look pretty different, but the base R hist Penguins $ bill length at the bottom has the fewest keystrokes and might be tempting to choose in this context. However, if you're thinking about choosing the syntactic structure for the entire course, then it's not just a decision to be made about a histogram in isolation, but rather it's a decision to be made about how we'll produce this and other data visualizations, how we'll do data wrangling, processing, or data intake, how we'll do modeling. And so if you think about the greater picture, maybe you still choose base R. That's great if that's what is consistent and what's appropriate for the context of the course. Or maybe you choose something like Mosaic that prioritizes formula syntax, or maybe you choose the piping syntax of the tidyverse. But the point is to make even these small decisions as one element in a larger picture of a syntactic structure to be used in a course. So for example, this is real code from a colleague that co-authored this presentation a few years ago. And this is in base R syntax. And the purpose here is to evaluate the difference in pulse rate between people who exercise more than 60 minutes a day and those who don't. So we're trying to analyze the difference in pulse. That's a variable in the NHANES data by groups according to exercise GT60. So these are the key variables in the NHANES data that we're using for this analysis. And you can see that, that we read in the data, we inspect the groups, we look at a couple of histograms, and then we calculate some summary statistics and execute a t-test, all of this in base R. If you wanted to leave this in base R, but try to make it a little bit more efficient in terms of the cognitive demand on students to process, to read through that code, then some simple changes like grouping operations that accomplish a similar task or are part of a greater purpose, like plot histograms. You can see in the middle groups 4 of these lines of code together so that we can see that we're organizing them, and then we plot these 2 histograms, and just packaging them that way makes it easier to see what's happening. And then separate that from compute summary statistics, where you have the tapply command. And I'll also add that we've added the name of the function fun argument in the tapply command. So even though we're adding characters to the code in that particular line, by naming the argument, it's less cognitive demand on the student who would otherwise have to be reading the tapply arguments, NHANES $pulse, NHANES exercise GT60, comma, describe, and recalling what the order of the arguments represents in terms of the purpose for those arguments. So by naming an argument, this is a way to help them manage the cognitive load. And so in some cases, adding characters reduces cognitive load. We've also turned on rainbow parentheses just to make it a little bit more clear how things are being grouped, in particular in the hist lines where you're plotting histograms. There are some nested parentheses, and so having rainbow parentheses just makes it a little bit easier to read the code and easier on the student to process what's happening. An alternative syntax borrowing from the Mosaic package prioritizes the formula syntax, and you can see that, for example, in the plot histograms, compute summary statistics, and carry out 2 sample t-test steps, what occurs inside the parentheses is identical. And so this helps to really direct the student's attention to what has changed, which is just the function in this case. That by using the formula syntax that can remain consistent within the parentheses, we can see that in all of these cases, we're doing something to compare pulse between groups from the NHANES data. But in the plot histograms, we're using GG formula to plot a histograms. We're then computing summary statistics with favstats and then carrying out the 2 sample t-test with t_test. So we're directing attention we're using the syntax and the consistent syntactic structure here to direct students' attention where we think it's most important for them for the purposes of the learning objective. So those are different paradigms, and they could be appropriate in different types of courses. And another consideration, even if we just dig into that histogram step a little bit more, again, recall that we had 4 different syntactic structures for producing a histogram from the penguins data. It's important to be thoughtful about the order that we teach some of these elements in the course as well. So are we introducing the variables, which then motivates a histogram? And so now we need the software, so we introduce students to R and show them syntax. Or have they already seen R and they're encountering these variables and they need to produce histograms? And so that's what's motivating us to teach them the syntax. So how it's introduced is another element for our consideration as we're teaching students about programming in a statistics course. Worked examples, live coding, or some combination all may produce different decisions, but the important part is that we're thoughtful about those decisions as we teach. So lastly, I'll mention that it's important to also model computational thinking norms, like debugging. It's part of the process to learn from our code and to encounter errors, and it's just part of problem solving. And so we need to normalize for students the emotional reactions to coding. If we only show them sterilized code that never throws or never produces an error, then they're not getting an authentic experience of programming. And so it's important that students see us produce errors and see that this is part of the process. In R, which is the language I mentioned that I teach programming with, the messages, warnings, and errors all often appear as red text in the console of the software. And I often tell my students that all of the red text deserves our attention, but not all of the red text is a bad thing. That's trying to normalize the emotional reaction. So we've included some questions to help you if you are teaching programming and want to be thoughtful about how to manage cognitive load and how to implement this as a learning objective efficiently for the sake of your students, as well as we've shared some resources. So these are available in the slides, which you can access on your own. And get some additional perspective, additional examples for introducing introducing programming, whether these are often R resources, but whether it's R, Python, or some other programming language, the principles we hope are portable for those teaching programming in a statistics course. Thanks very much.